All right. Hello, everyone. We are so excited to get started. Thank you for joining us for Planet Fest 2021. It is my pleasure to welcome CEO of the Planetary Society, Bill Nye.
Greetings, everyone. Greetings, everyone. Welcome, welcome. I hope many of you enjoyed sailing the light about Light Sail 2 and the Light Sail program. And it's just really an honor to be addressing you today. This is our 10th Planet Fest. And everybody, the society goes back 40 years, and we have Planet Fests at opportunistic times when there's something cool going on in space that we can celebrate here on Earth. So if we could just show that first slide, I'd just like to remind everybody that the society was founded in the winter of 1979 and 1980 by Bruce Murray, who was the head of the Jet Propulsion Lab at the time, Carl Sagan, who was a very well-known astronomer and remarkable author, and Lou Friedman, who was an orbital mechanics guy working at the Jet Propulsion Lab at that time. And they founded the Planetary Society because they felt that the public interest in space was very high, but government support of it was not especially high. So after they founded the society, the Voyager spacecraft, two of them had launched. And understand, everybody, they launched in 1977, the year after I was graduated from engineering school. And I got a job at Boeing working on 747s. And as I like to say, don't worry, I was very well supervised. But the first Planet Fest was in 1981. If we can get that next slide, it's the cover of the Planetary Report, which we still publish in paper and online. And so this is the 40th anniversary of the society, and it's our 10th Planet Fest in the 40th year. That to me is just wonderful and remarkable. And so as you may know, I joined as a charter member in 1980, and I was in class in the spring of 1977 when Carl Sagan was asking, what should we put on the Voyager record? This should be the records that go on the Voyager spacecraft that go off into deep space, leaving the solar system now, beyond the heliopause, beyond the farthest place that the sun has its strongest influence. And he wanted to put a rock and roll song, and he wanted to put Roll Over Beethoven by Chuck Berry. And at that point in the semester, people are so confident they don't come to every class. I came to every class. And we all said, no, Professor Sagan, no. Come on, it's got to be Johnny Be Good. So then sure enough, you guys, at the next Planet Fest in 1989, if we can get this last slide, I just think this is charming and wonderful. Chuck Berry and Carl Sagan were on stage together celebrating Voyager's flyby of Saturn. And, you know, if you ask many people, what's your favorite planet that's other than Earth, a lot of times they'll say Saturn because it's so beautiful. So I just wanted to share with you all what an extraordinary thing it is that the Planetary Society was founded with this principle. And this principle still drives us to engage people all over the world in the enterprise that is exploring the cosmos. We want to know our place within it. We want to find out, as Bruce Murray so eloquently said so many times, where did we all come from? And are we alone? How can you not help but ponder if there aren't other species out there in the cosmos? Now, when I was in school at that time, Frank Drake was also on the astronomy staff at Cornell University. And this is when he invented the Drake equation, this famous cool thing, just pondering the likelihood of someone else being out there. And when I was in school, people speculated that perhaps there was a planet around every 100 stars. So 1 in 100 stars would have a planet. Well, now we're pretty sure that every star rather has about 10 planets. That's a factor of 1,000. Like we feel that it's more likely than ever. And so one of the things we talk about all the time at the Planetary Society is the future. Now, Lou Friedman led us, the guy in the picture on camera right there, led us for 30 years. I left a meeting at the board of directors and I came back. They had taken a vote 10 years ago and now I'm the CEO. But the future is really exciting. You know, when Planetary Society was formed, here were Voyager spacecraft. The first Viking 1 and 2 had landed on the surface of Mars, sent back the first pictures of Mars. This is an exciting time. The next rover, the next mission to land on Mars wasn't until 1997. 17 years later, you know, almost 20 years later. But with that, that was an exciting time. But my friends, this is the most exciting time. What's going on in space right now is the most exciting time that we've ever had in planetary exploration. The missions that are planned and the missions that are out there. Congratulations to the United Arab Emirates, the Hope spacecraft's in orbit. Congratulations to the Chinese Space Administration. Tianwen-1 is in orbit around Mars. And next week, I hope you all join us again for our landing party when Perseverance lands on Mars. So everybody, in order to have a future, an organization has to have new people joining it. And I'm reading the text here. So many of you have joined us in recent years. And thank you. We're to the point where more people join electronically than joined in the old days by paper mail. And so I am thrilled. And along with that, we have one of the world's foremost authorities on planetary exploration, one of the world's most eloquent speakers, one of the world's most revered professors of planetary science, who is now our president of the board. And it is my honor to now introduce you someone who is an expert on the planet Mars, our new president, President Bethany Ehlmann. Take it, Bethany. Oh, we need audio. We need audio.
Thanks, Bill. I appreciate the introduction, and I'm delighted to be here. Welcome to Planet Fest. Let me just get my screen set up to share with you the presentation that I'm about to give here. So I'm welcome, and I'm delighted to talk to you about one of my favorite topics, which is the exploration of our closest neighbor, Mars. So it's been quite a year, but I hope that even amid the trials of 2020, that we have all been able to take a moment and do one thing that we certainly can do, no matter where we are, no matter the state of affairs elsewhere in the world, which is think about our place in the cosmos and stand for a moment just in awe that we are this one planet among a vast sea of stars and planets. It's this appreciation for the cosmos. That's why I explore. It's, I think, why you explore, why you are on and celebrating on this Planet Fest, that we can have these moments. My own moment in space began when I was a student in 2004. That's when I became a member of the Planetary Society, and I was drawn into exploration by a mentor at my college, Ray Arvidsson, who introduced me to exploring Mars via Spirit and the Opportunity rovers. I just loved that we cannot at this moment send humans to Mars. It's there, it is the future. But this is as near as we can get. The rovers are our proxies. Their shadows on Mars are, in fact, our shadows, are our exploration. The question that, as a scientist, I find most intriguing is I think about the cosmos and think about exploration, are questions that actually relate very much to this picture, to our Earth, to this spectacular image from Apollo 8, which is, why are some planets habitable? Water, atmosphere, climate, they sustain life for billions of years in a way so stable that they can give rise to intelligent life like our own that can then ponder these questions. The juxtaposition with the lifeless moon really brings home the question of how special is our Earth? How does our own Earth work? Why and how do certain planets sustain habitats over time? Of course, in our own solar system, there are three really that we can think about these questions, three that are rocky with atmospheres: Venus, Earth, Mars, all lie in a zone that approximately allows liquid water to be stable. Mercury is too close to the sun, but these three are in the so-called Goldilocks zone, yet only one is, as far as we know today, an abode for life. So the question is really why and how and why did this change? Now, this is complicated, this plot. But what I'm showing you, maybe too complicated for a Saturday morning, but what I'm showing you is time. It's the arrow of time over 4.5 billion years. The oldest rocks on Earth are from 4.5 billion years. The oldest fossil life from 3.5 billion years. There was a lot going on at the solar system at the time. The sun was fainter. Impacts were bombarding the planets. But on Mars, there were lakes, hydrothermal systems, groundwaters. I'll talk a little bit about that later. What's extraordinary is that on Earth, there's only 1% of this critical period from the first billion years. Only 1% of it is preserved for us to explore and understand the origin and evolution of habitable worlds. But on Mars, it's there. It's there at the surface, exposed for us to explore. So the question is, what sustained these conditions? And then why? Why did Mars undergo this massive climate change to the drier planet we see today? And along the way, what happened to any potential Martian life? Was it there? Did it develop? Is it still there? We are right now in a golden age of Mars exploration. You know, we're now in kind of the 50th year. The legacy began in the 1960s. It had continued on with the successful Viking landers. It was a bit rocky in the 1980s and 1990s with a kind of a dearth of missions and a few failures. But from the 2000s onward, not only NASA, but the European Space Agency, India, it's been a success, and it's been success after success. And we have tremendously expanded our understanding of the planet by this coordinated set of exploration by multiple nations. So I'm going to begin the tour of Mars. This is supposed to be the Mars mind meld, right? So let's get Martian. Let's ask the questions. On modern Mars, could it be habitable? Could there be life there today? What is modern Mars life if we were to stand on the surface? Well, here's a picture, and it's an oldie but goodie from Viking. You can see a piece of the Viking landing hardware out on the frosted plains of the northern lowlands of Mars. And yes, that is frost. So we have Mars, the red planet, but early in the morning, water frost on the surface. So Mars is like Earth in that it's, you know, tilted on its axis. It has 4 seasons as it goes around the sun, but it's not like Earth in that its atmosphere is pure CO2, but less than 1% of the thickness. The surface temperature on Mars goes so cold that CO2 freezes out of the atmosphere at the poles. Although interestingly, it actually gets quite warm, you know, a balmy about 70 Fahrenheit during the day at the equator. But the surface temperatures fluctuate in extreme because of this thin atmosphere, and they get cold because Mars is twice as far from the sun. Cold, dry, colder and drier than the Antarctic dry valleys, which are the closest analog on Earth. Yet, this is interesting, right? It's full of water. Was water once liquid? Well, how much water is there anyway? We know from the Phoenix lander that in some places in the northern lowlands of Mars, ice is just barely beneath the surface, centimeters beneath the surface, blown away by the by rocket thrusters. We know also that Mars has water ice clouds, and we're able to monitor them with our rovers, like beautifully watching the clouds go by in the Martian landscape. We also know that sometimes there are fogs that fill the enormous Valles Marineris Canyon system, tens of times larger, deeper than the Grand Canyon. It fills with a water fog. And in Valles Marineris and in other regions, we see these enigmatic dark streaks extending, lengthening, flowing, perhaps extending downhill at the times of the year where it is the warmest. Is this water? Is this salty water? Is it water that could sustain a habitat today? So the real question in modern Mars is, why is the climate the way it is? Where is their water? Where is their water stable? So Mars today, and this is also a tricky plot for a Saturday morning, but you are looking at temperature on the x-axis, vapor pressure on the y-axis, and I'm showing you where water can be stable as a liquid in that field called liquid. Now Mars today, only for a few weeks of the year at a few parts on Mars is the pressure high enough and the temperature high enough that water is even stable for minutes against sublimation. So today Mars is right on the edge of being able to have water, of being able to be potentially habitable. But now let's talk about time. Let's think about time. Let's think about not this snapshot of today, but what the past holds. And let's stick with the recent past. Now I'm a geologist. So for a geologist, the recent past is not like 10 years ago. For a geologist, the recent past is, just a few million years ago. So let's talk just a few million years ago. Something to know about Mars that is very different from Earth is that Mars is right now tilted at about the same. Mars is tilted at 25 degrees on its axis, Earth at 23 degrees on its axis. But the thing about Mars is Mars wobbles. Mars is a wobbly top, and Mars is not always tilted to the way we see it today. If you look back at the past record of the word is obliquity, but that tilt of Mars on its axis, it's at around 25 today, but you can see that even less than 100,000 years ago, that tilt was very different. So Mars is tilting up, down. What does this do? Well, this moves where the sunlight is hitting on Mars. It changes whether Mars can have polar caps. You see the polar cap there in the bottom of Mars, bottom and top of Mars. Where those caps are stable all depends on the tilt. And it's extraordinary that when we peer into these caps with radar, we see layer upon layer, layer upon layer of history recording this changing tilt. And in fact, in the South Polar Cap, have discovered that it has trapped, buried under ice, enough CO2 ice that if released, it would more than double the atmospheric pressure of Mars. How did it get there? Well, it was during one of those obliquity cycles. The CO2 ice, it got cold enough to condense down, and then the water ice covered it up, trapping over half of the Martian atmosphere. Why does this matter? It matters because it all goes to stability. If Mars tilts again, tilts straighter up and down, those volatiles, that CO2 is released into the atmosphere, and what it does is it expands the availability of potential liquid water on the surface. So key finding of this decades of golden age of exploration, the Mars surface environment is not stable. Unlike Earth, it has this perturbation caused by the orbits of other planets, in particular Jupiter. So it's perturbed, it's not stabilized by a moon. And then secondly, Mars has often, in fact, recently, been a more favorable place for liquid water than it is right at this moment. Do we see evidence of this? Yes. The Spirit rover, digging in the soils, uncovered salts. Salts, not, thick layers of sulfates and chloride salts, not even, a couple inches below the surface, formed when there was once ice, or maybe even liquid water, that then sublimed into the atmosphere, leaving behind this lag of salts, like if you let a pan of salty water crystallize out on the surface. We see this evidence of recent climate. The question, of course, is what does this mean for life? On Earth, microorganisms can be dormant for hundreds to thousands of years in salts. What are the limits of life? Can it do such a thing on Mars? This is one of the key questions as we explore. So we know that Mars right at present is right at the edge of habitability. In fact, it may go through perturbations that take it in and out of being able to support life. But what about the past? What if we peer back further in history? Well, we've been able to do that with the fleet of orbiters around Mars, taking images at ever higher resolution. Here we're zooming into the fracture systems just north of where the Perseverance rover may land. As we peer at rocks exposed by faults and then eroded by water, we can take a look at the infrared wavelengths of light, painting a picture of composition with these false color images, these infrared color images of the Martian surface that reveal layer upon layer of rock, each preserving a different environment. A different color here means a different mineral. Blue in this composite I've put together means a clay mineral, a mineral formed in water. And you can see this these spectacular ridges coming up in this clay unit, these crisscrossing hardened ridges capped by volcanic materials above. What are they? Well, what we're seeing is in fact the plumbing of a Martian groundwater system. We're seeing a spectacular mineral and climate record preserved that records the groundwater what that was once beneath the surface. Not only does Mars have surface expressions of water, and we'll talk about those in a moment, but what we're seeing is also eroded, preserved in the rock record, the deep plumbing of the Martian system. Now, aquifers like this host life on Earth. So again, the question is, if we explore, what will we find? Now, this is one spot on Mars. This is a map of different minerals, each of which records water. I've laid out the planet here on a topographic map. At the north and the south, dust cover kind of precludes us taking a look with our orbiters from the surface. But in the mid-latitudes from about 50 degrees north and south to the equator, we can make spectacular maps from orbit, taking images like what I showed here. Each of these dots is a different location on Mars where I could show you a similar video zooming in on the detail of this record of habitable environments. And what we can do, though, is for a few, only a few of the thousands, we get the choice. We can choose to send a rover to explore. Now, we've only able to do this for so many. There are at least a dozen types of habitats. We've only visited a few, but we have learned so much, and we are learning now, not about recent Mars. We're learning about Mars at these sites, the Mars of 3-4 billion years ago, the Mars that was once a lot more like Earth. Why do I say that? Well, I say that because the Spirit rover at Gusev crater touched down, and in its fourth year of exploration, made it to a feature called home plate, which had these spectacular nodular rocks that the chemistry showed was 90% opaline silica. Where does something like this form? Well, it forms in the types of environments we see around hydrothermal systems today, in Iceland, in Yellowstone, around volcanoes, spectacular hot springs depositing minerals full of silica. If we go elsewhere on the planet, the same year, the Opportunity rover touched down, hitting an interplanetary hole-in-one in Eagle crater and seeing beautiful layers of sedimentary rock exposed. In the lower left, you can see the ripple marks, ripples preserved from ancient Martian lakes, preserved in these sandstones. Now we know, though, because we went there, visited on site, that this would perhaps not have been the most pleasant environment. pH of less than 1, acid waters nonetheless, but pH less than 1, that record preserved in the minerals. Would this have been a source for life? Well, on Earth, life finds a way. Shallow seasonal lakes, such as what we see in Western Australia or the western deserts of Utah and Nevada, do in fact host salty lakes, sometimes acid lakes with life. The lakes got a lot fresher when the Curiosity rover landed at Gale Crater. And here we see the layers of the lake system preserved year after year, season after season, preserving layers one after the other, run after the other. The payload of Curiosity showed that these were clay-rich, and here the waters were neutral to alkaline in pH. And the water seems to have fluctuated, sometimes quite shallow, sometimes quite deep. So as you envision what the rover was traversing over, waters coming and going, overtopping sand dunes, and then the sand dunes come in. Then the water rises, repeat cycles, but in this case, of a very freshwater system that you might have wanted to take a swim in if you had found it on past Mars. A key finding coming out of the Curiosity mission, one of the key findings of the last decade of exploration, is the discovery of organic molecules in these mudstones in this lake. That's important because organic molecules are the building blocks of life. They're also potentially fuel for life, right? We eat organic molecules daily to sustain ourselves. And these were there. These were there in this habitat and are preserved. So, finding multiple aqueous environments of the planet, multiple types of Earth-like habitats with organic matter up until at least 3 billion years ago on Mars. And then the climate changed. We are, as we explore, as we build our knowledge, as we visit site after site, we are on the path to solve these questions about climate change on Mars, about life on Mars. The questions are, how did Mars sustain this warm climate? You know, almost twice as far from the sun as Earth, so much less sunlight, yet lakes, rivers, hydrothermal systems, did those have life? And then why the change? Why the change from environments that were clearly abodes of life to the colder, drier planet on the edge that we see today? So as we continue to ask these questions, we consider the future of exploration. What is the future of exploration? Well, it's been a great week for Mars. For any of you who have been watching the news, the fleet of spacecraft at Mars is now 10. You can see them on the white text here. They are represented by the InSight lander, the Curiosity rover from NASA, and then 8 orbiters spanning NASA, the European Space Agency, India, and then 2 nations joined the fold of explorers at Mars this week, Tianwen from China and the HOPE mission from the United Arab Emirates. So it's a great time. The golden age of Mars exploration continues. We continue to build different types of science exploration. Europe has its next rover planned in 2022. China will in May attempt to land a rover released from its orbiter. But the upcoming big event, one of the drivers of why we are having Planet Fest here, why we are having it now, is the Perseverance Rover, the 2020 Mars rover mission, scheduled to land on Thursday around noon Pacific time. So let's talk about what Perseverance will reveal. One of the key aspects of Perseverance is that it's not only an explorer, it's a cacher, it's a driller. So it may look like Curiosity, but when it extends its arm out onto the surface and it reaches out to the rock to collect samples, it is not just drilling to bring samples, bring rocks to its laboratory to analyze on Mars. It is collecting them, stowing them, because we are going to bring them back to Earth. So consider that for a moment. So the tube, the sample that's sequestered gets put in a carousel that then gets transferred into a cache held in the belly of the rover, where the tube is deposited for in a canister for future return. This will be the first time, this Perseverance is the start of a journey where for the first time, we don't just leave our spacecraft on Mars, we bring bits from our exploration back, similar to the way the Apollo astronauts returned samples from the moon. So what does Perseverance bring? How does it explore? So Perseverance has a set of multiple science instruments, a mast with a camera, a laser for chemistry, a spectrometer for mineralogy, a weather station, a subsurface radar, a system to produce oxygen, and then on the arm, a detailed set of instruments to select the best cores, to drive up to a rock, select the best cores to cache and to bring back. Another exciting aspect of 2020, and one that I'm particularly looking forward to, is that we anticipate that this will be the first planetary flight. 2020 also brings the first Mars helicopter, the Ingenuity helicopter, a technology demonstration to demonstrate that we can fly on Mars and use that to explore and expand our footprint. The caching part is, as you saw before, the goal of Perseverance is not only to explore, but it is to collect rocks about the size of a piece of chalk that are then sealed in a sample tube and that are then placed in a canister for future return. So how do we do this? Where are we doing this? Why are we doing this? Well, we're doing this because this is the best way to get at those answers about Mars climate change, and to look for Martian life. So the landing site selected is actually a landing site that's quite special to me personally. When I started as a first-year graduate student at Brown University, it was just as the Mars Reconnaissance Orbiter was entering orbit. The cover popped successfully off the XRISM instrument the third week that I was a student. And one of the places I was privileged to work on was the Jezero crater. And so you're seeing here as a background some of the spectacular data at 5 meters per pixel, half a meter per pixel from the orbiters that we were able to pair with infrared composition to investigate what you see, this feature circled on the right-hand side in red, this beautiful delta environment. There's an incredible journey of exploration because the rover will land just to the left of the J in Jezero in the red circle at the bottom of the crater, and then we'll trek up through a delta that formed in a past lake up out to the watershed to another ellipse where the samples will be collected by a fetch rover. Why is this important? Why is this trek important? Why not just grab and go? Well, it's because if you collect while on a hike, effectively a Martian hike, what you're doing is, like, if you were hiking in the Grand Canyon, you're walking through successive slices of Martian time. So in Jezero crater, we capture the last episodes of a former lake, about 3 billion years old. But as we trek up through the channel, up out of the crater to the rocks that were eroded by the waters feeding that lake, we go 1 billion years further back in Martian time, to the time of early volcanoes, giant impacts, and those preserved hydrothermal systems from Mars's deep plumbing that, perhaps like hydrothermal systems, could host life. So we get to explore multiple habitats: lakes, rivers, hydrothermal systems, all of them in the search for life. This is just a zoom in to show the detail of the exploration that awaits. So on Thursday, Perseverance will either land on the top of this delta or just at its toe. You can see the western channel that fed former Lake Jezero, spreading this out. Everywhere you see green, that's a lake sediment with a clay or a carbonate. Somewhere neutral alkaline lake waters, again, that you'd probably want to take a swim in if you came across it. So that's what we're going to be stepping through, exploring. And this high-rise image taken at 25 centimeters per pixel just shows the level of the level of detail in the rock record and the landscape that we will be visiting. Now, with our microscopic imagers on the rover payload, we're able to get up close and personal to pick the samples. What's shown on the left are not Mars rocks. What's shown on the left are Earth rocks. They're some of the earliest life, called stromatolites, microbial mats that grow in the shallow waters of a lake. The rover has 2 instruments, Sherlock for mineralogy and organics, and Pixel for chemistry, that will allow us to trace the best places most enriched in organics, most enriched in minerals to bring back in our sample collection. So Mars 2020 is really the first step. It's the first step in what is one of the most ambitious endeavors ever undertaken in planetary science. That is sample collection by Mars 2020, and then later missions that will land a rocket whose fate is to be delivered those samples and then launch back from Mars to deliver those to an orbiter that captures the canister, brings it back from Earth. So the 2020 mission is the start not only of an exciting journey on Mars, but an exciting journey of these rock samples to bring them back, to bring them to Earth. Because what we learn in our labs, the Apollo samples that the astronauts, that robotic exploration first actually, and the astronauts got back are the gift that really keeps giving to science. As our technology gets more sophisticated, our examination gets more sophisticated. To look for life, you need to be able to look for isotopes. You need to be able to get down to nanometer scale. We can only do that in our labs. So these samples are ones that will answer questions about climate, about life, and they are really a pathfinder for what we hope to one day do, which is send humans to the red planet and then bring them back. I hope one day, as I think about this often as I explore with rovers and as I look forward to what we will do with 2020, I think about what we could do with humans on Mars, exploring, actual geologists in person on the ground, interacting real time with these rocks, making decisions, collecting samples. I would love to be the person on the right. I hope that some of you listening today, maybe some of the folks my age, kids that are listening, I hope that one of you who are listening today is that person on the right-hand side of the screen, the Martian geologist looking at the rocks. So with that, I'm happy to end. I hope I've given you a flavor in this mind meld with Mars, that Mars is a planet right on the edge of habitability today. It once hosted them. We have some key questions and key milestones ahead of us for exploration. And until we get there ourselves, the rovers are our proxy. So I hope you enjoy the rest of Planet Fest, this celebration of exploration. And with that, I'm happy to take any questions about Mars as we kick off this exciting weekend event.
Bethany, that is just fantastic. It's just, you guys, it's so exciting. And the reason we study Mars so carefully is because it's right on the limit of something that may have been alive there. Everybody, I say all the time, Bethany, you've heard me say this a zillion times. If we were to discover evidence of life anywhere on Mars, Europa, in the Venusian atmosphere, some aeroplankton things giving off phosphine gas. Whoa, really? Well, maybe not. Well, maybe. I mean, it would be extraordinary. It would change the course of human history. And you all would be part of it. You all supporting the Planetary Society, supporting President Bethany Ehlmann and everybody. You are part of this larger thing. When we think about the history of astronomy, which everybody likes to say is humbling, the more you learn about your place in the cosmos, the more you realize what a small part of it you are. But on the other hand, that we can understand it is, well, it's astonishing. And so if we were to find evidence of life on Mars by bringing these rocks back, these samples, you all be proud. We would have changed the course of human history in a way that Galileo, Copernicus, say what you will about them, Columbus did, Magellan did, in a way that's just hard. It's really hard to imagine how profound it would be. And so along that line, Bethany, we've had several questions about taking plants to Mars, about you guys, we prefer the word settlement of Mars to colonize, because colonies have gotten a bad rap with, understandably. Let's just call it humans to Mars versus looking for life. What steps, Bethany, do you all take to keep from contaminating Mars before we send people there? And do you think it's worth it all?
Well, I absolutely think the exploration is worth it all. And in terms of, I guess your question is a question about planetary protection. So what does that mean? That means when we bring back samples from other worlds, from Moon, asteroids, Mars, we make sure that they are not harmful to Earth, and we treat them with care until we are sure of that fact. So that is one facet of planetary protection that we are absolutely doing for the samples that are being brought back from Mars 2020. They will be going into class 4 clean rooms prior to being distributed. But then the other question is the part of planetary protection where we are actually protecting other planets. From what? From us. Not exactly from us, but from the life that we might bring from Earth that could forever contaminate that planet in a sense. I mean, some of you are probably familiar with invasive species, right? They come in and then they sometimes take over and become a problem. Well, really, we have one chance sort of in our solar system for each planet. We kind of have one chance to really ask and then answer the question, is there life there now? And it would be a sure shame to bring Earth life, not know it, the Earth life takes over, and then we discover that and we wonder, well, was there ever Martian life? So this is why planetary protection is so important. The sample tubes, everything on the rover that touches the surface, the sample tubes, they're sterilized, they're swabbed so we know what we're bringing, if anything. So we are taking great care, because we want to be sure that we're preserving that opportunity for exploration, that opportunity to make what would forever be a paradigm-changing discovery of life on another planet.
So you guys, I am so old. I remember very well when Apollo astronauts, and I'm going to say that if I get it wrong, bust my chops, I think it was 15, went over on one of the lunar rovers, a dune buggy on the moon, drove over to one of the Surveyor spacecraft. Now, you know, when people first landed on the moon, there was speculation that the dust would be so fine. How fine would it be? It would be so fine that anything that landed there would sink into the lunar surface. So 2 spacecraft were sent to land there, the Surveyor with the right amount of mass and the footprint of the foot pads to determine whether or not it would sink, among other things. Anyway, astronauts went over there, took a piece of the Surveyor spacecraft off, brought it back to Earth, and there were microbes. Oh my goodness, there was something alive. And then, so the question was, could something survive on the moon all that time? It turns out, well, we'd contaminated it. The thing wasn't, the test wasn't very accurate. The was not an extraordinary finding. It was kind of a mistake. And I just really emphasized to everybody listening just the astonishing nature of a discovery of life on another world. Now, along that line, Bethany, if you'd answer a couple, we've had several versions of this question. What's going on with the methane? The Curiosity rover. How long is Curiosity going to last, by the way?
Yeah, well, just to amplify what you're saying, I mean, this is why we explore with care. We've learned a lot since those first days of Apollo. All right, what is going on with the methane? Well, first, I guess I should tell the whole group what the story is with the methane and why people are talking about it. So methane is a gas, right? CH4.
Well, it's AKA swamp gas. It's what bacteria give off. It's what comes out of your tummy. Yeah.
And it is not stable on Mars today. Mars's atmosphere is oxidizing, lots of CO2. Methane gets destroyed, right? Except missions, telescopes from Earth keep seeing whiffs of methane. Maybe the most like, and then gone, and then gone. We're talking about low parts per million, parts per billion, coming, going. So what the heck is up? Well, it's been a puzzle because the Curiosity rover sees this very small, seasonal, but very regular variation in the amount of methane in the Mars atmosphere. Occasionally, I think on 2 occasions, you'll have to fact check me, it's 2, but there have been spikes where it's, quadrupled, quintupled, and then it's come back down. Okay. Now, Europe sent an orbiter, the trace gas orbiter. What does trace gas mean? Gas there in tiny amounts. Europe sent the trace gas orbiter in part to understand what is going on with methane. But guess what? The trace gas orbiter has not even seen the methane. It has said that there is a lower limit of like parts per trillion. It doesn't see the methane that Curiosity sees. So what is happening? Well, this is science. Either there's something funky with one of the instruments and there are teams of people devoted to figuring this out, or the other possibility that is I think most likely is that the methane is sort of localized in the region around Curiosity in the bottom of Gale crater, this 70-kilometer crater. The trace gas orbiter cannot resolve tiny little pixels of methane. It measures over vast swaths. And it also can't resolve, this far upper meter off the surface. It sees through, hundreds of kilometers of atmosphere. So if the methane is there, an explanation that would reconcile this is that the source is somewhere around or maybe even in Gale crater, maybe underground. There is relic methane being released, or maybe small amounts of water rock reactions creating it, maybe life creating it. It's important because methane is only created by reactions from active volcanoes, active water, life, or any of these things happening in the past and somehow the methane getting stuck and only being released now. So this is a mystery. It's one of Mars's biggest mysteries of the moment.
Let me ask you a detail, Bethany, thinking out loud. Everybody, that periodic table is from the old Science Guy show. Hangs in my office. Carbon, number 6, it's got 6 to start with, 6 neutrons. And so if you have methane, there's 4 hydrogens around. CH4, all right. Carbon dioxide, it's carbon with 2 oxygens, and they're going to have 8 protons and 8 neutrons. That's going to be 16, it's going to be 32. So in other words, just thinking out loud, methane is a lot less heavy or less massive than carbon dioxide. Would we expect it to get squeezed up to high in the atmosphere, and by the time it gets up there, it's so diffuse, the trace gas orbiter can't find it? Is that right?
This is part of the puzzle, right? Because maybe it's dilution, right? Maybe there's a source near Curiosity and it's being diluted by diffusion to the point that it's not seen. So yes, chemistry, morning chemistry lesson, courtesy of Bill Nye. This could be the explanation, and we need more measurements. We need more exploration to figure it out.
So everybody, I can't help but wonder, is there some slush, some liquid water just below the surface in Gale crater, and there are microbes chewing away? And so we just happened to put a rover down after you guys worked to pick a landing spot. We happened to put a rover down in the very, very last Martian swamp. Whoa.
It is one of the deepest, Bill, it is one of the deepest holes in the ground on Mars. So if there were a Martian swamp, it would be at Gale.
I mean, that's, you guys, that's just amazing. And so, there's a lot going on here. Relative to where Curiosity is on Mars, where is Perseverance going to be? And then where is Tianwen-1's rover going to be?
Yeah, so Perseverance is landing, go about 90 degrees or so, still near the Martian equator, but go about 90 degrees further to the, you have a convenient globe of Mars. Maybe I should get one from my office. I could even point this out. I think I'm going to try this in real time.
And I have one hanging from the ceiling too. Oh, you guys, this is fun. So for those of you who are
Real-time
joining,
science, real-time
and
science.
Dr. Ehlmann, this is
right,
the world's
let's do
foremost authority, everybody.
Let's
We're
do it.
not messing.
All right, the Curiosity rover is going to land here, has landed here. This is Gale crater. And now if we rotate Mars, I actually even have a little orange thing where the Perseverance rover is going to land on the Isidis Basin, which some people hypothesized was the edge of a Martian ocean. But we're going to land in what was certainly once a Martian lake. Tianwen, I'm not 100% sure. Tianwen, I believe, is landing in Utopia Planitia, last I heard, which is right here. It's sort of actually in between Gale and Jezero, and Tianwen is going to go somewhere up in here. It's a low, flat place, so a good spot to do a first Mars landing.
So understand, you guys, this is extraordinary, where the Chinese Space Administration is participating in this global effort to explore other worlds. Now, everybody, there's a lot going on in politics, my goodness, right now, but this is another example where space exploration brings out the best in us, not just technically, where we solve these amazing problems that have never been solved before. How do you sterilize a chalk-sized, cigarette-sized, golf pencil-sized rock thing on another world? Okay, that's technically amazing. But also, where scientists are going to share these data, the pictures, the measurements of methane, the measurements of composition of rocks. They're going to share these data, and it is, I'm telling you, it's to the good. That the more people around the world work together, the more in common we will find that we have with each other, and ultimately, the better the world will be. I mean, it's just, as my mom said all the time, common sense. It's not that common, but by participating, getting everybody to participate, we're going to make the world better. And as I say, if we make a discovery, some discoveries that will change the world, it would be pretty good also. And there've been a lot of questions about politics, policy, and investment. Everybody, stay tuned to the sessions about policy. We have two of the world's foremost authorities, informed by people like Dr. Ehlmann on our board of directors, who are experts on space policy, who've spent their lives studying it. Brendan Curry, Casey Dreyer are experts on NASA space policy, especially, and the significance of NASA. You guys, no matter where you're tuned in, welcome. Just NASA is so big compared to the other space agencies. It's important to keep an eye on what they're doing. But the reason you invest in space exploration, whether you're the US, China Space Administration, Canadian Space Administration does fantastic stuff, European Space Agency, amazing, JAXA, Japanese Aerospace Exploration, Vietnam has a space program because it brings out the best in their society. It's where you engage people at a very high academic level, and you make very small investments that have tremendous technological benefits. There's a very easy argument to make that we wouldn't have the internet without the Apollo program. So the internet has affected everybody in the world. So let's see, Bethany, I am charmed. I have always been charmed by the expression, the Noachian. How do I say it? Noachian?
Got it, Noachian. Like
so this
Noah.
is Noah. Noah's got an ark and he's swimming around on Mars. That's where it's a whimsical name.
It's a good way to keep in mind the name. That's not actually where it comes from, but it's a great way to keep it in mind because that is Mars's warmest, wettest period.
And so when was that in relative to, well, when was that in Earth years?
Yeah, about 4 billion years ago to a little less than 3.5. But oh, I see Danielle's coming online, which might mean our conversation needs to draw to a close.
Well, everybody, I just want to thank you. A lot of the questions have been along similar lines, but they're about, as far as I can tell, Bethany, Danielle, the questions are about the relationship between life here on Earth and what may be life elsewhere, especially Mars, because it's nearby. And just, you guys just noticed very recently, evolutionary biologists have pushed the origin of life here on Earth farther into the past. Now people think it's about 3.75, 3.7 billion years ago. When I was young, it was, 2.5 or something. And this sounds like just throwing around huge numbers, and we are, but Mars is smaller, cooled off faster, had a Noachian period before the Earth did. So it's reasonable that life started there first. Wow. All right. And so everybody, I claim that we would not be exploring Mars with 10 spacecraft right now, were it not for the work of our founders and all of you. That the Planetary Society does these three things extraordinarily well. We educate. That's what Dr. Ehlmann's been doing the last half hour, showing us all learning about these extraordinary discoveries elsewhere. We innovate. LightSail 2 is flying and taking these amazing pictures right now, and you funded that. And we are learning stuff about flying solar sails that would not have been possible to learn. By the way, we're in Earth orbit, you guys. The LightSail 2 isn't powerful enough to take us beyond that, but it's how we learn to maneuver faster than any other, higher performance than any other solar sail so far. And then the other thing we do is we advocate. We advocate around the world in space agencies and administrations, and especially here in the United States. And so we innovate, educate, and advocate, and it's all thanks to you. So thank you all very much. Enjoy the rest of the conference. I'm going to step aside until the gala, when we're going to get dressed up and enjoy some exciting Why I Love Space messages. I'm looking, Dr. Ehlmann, Madam President, thank you so much. I'm shutting off my camera. Over to you, Danielle.
Thank you. Thank you. Thank you so much, Dr. Bethany Ehlmann. That was such a great way to kick off this weekend of learning and celebrating. I'm Danielle Gunn, Chief Communications Officer here at the Planetary Society. And on behalf of all of us who work here at the Planetary Society, thank you so much for being here with us today. It is so special to connect with you, our members and our supporters, because it's been a rough year for all of us. And so to have this moment, it's been incredibly fulfilling and heartwarming, and it's only just started. So it's just amazing. This conference is unique because, one, it's our first ever all virtual Planet Fest. But what's really unique is that it's a conference designed for space enthusiasts. It's not a professional work conference. There's no prerequisite that you have to work in the space industry. The only prerequisite is you love space. That's the only requirement. And so the folks that are here today, all of you, you're here because you love space so much that you want to do something with your enthusiasm. So I hope you walk away from this weekend feeling excited and prepared for this Mars milestone moment and fully equipped to spread the joy of space exploration with others. Whova is the app that we are using. You are in it now watching this. On the left side, you will see your agenda. You can click into the sessions and join the chat. You can also see our exhibitors and our sponsors. There's also a mobile app that has a few extra features. It has a photo contest. There's a leaderboard to see who's engaging the most. And so I encourage you to check out all the other things that are happening inside of Planet Fest in addition to these sessions. I'm going to wrap it up here, but I just really quickly wanted to say thanks to our sponsors, Movaglobes, Matrox, Hypergiant, Celestron, Cafelli, Omaze, and Penguin Random House. And let's go over to the next session with Matt Kaplan to see everything that we don't know about Mars. Thanks so much, everyone.